We're going to stick with the theme of comparing reactions of alkenes to reactions of alkynes and look at hydroboration oxidation of alkynes. We just got through talking about hydration of alkynes that yields ketones. So what happens in hydroboration oxidation of alkynes? Well, let's think about what happens in the hydroboration oxidation of alkenes. Remember we said that alkenes undergo hydroboration oxidation to give us anti-Markovnikov addition, where you get the least substituted OH, alcohol forming. Well, like alkenes, alkynes can be hydroborated. And like alkenes, the stereochemistry of that hydroboration is certainly going to be syn addition. And so what do we mean by that? Well, the hydrogen and the boron add to the same side of one another. And of course, the regiochemistry is the same. The boron attaches to the less substituted carbon. So what I can do with that is I can take an alkyne, right? Generally speaking, I'm going to be using a terminal alkyne where you have a hydrogen as one of the groups coming off of the triple bond. And I'm going to react it with a sterically bulky dialkylborane. Now the reason for this is because, I don't remember in the hydroboration reaction you tend to get dialkylboranes and trialkylboranes involved in that process. So I can basically limit the number of times that alkylboration occurs, that hydroboration occurs, excuse me. And so I end up getting this. Notice the hydrogen has added to the carbon with the R group, and the borane has added to the least substituted carbon. It is a syn addition. The hydrogen and the Br2 add to the same side. Now, when I oxidize that alkylborane with hydrogen peroxide, it yields an enol. That enol then tautomerizes to an aldehyde, right? So if I start with this alkylborane, I add hydrogen peroxide and sodium hydroxide and water, I get an enol, so I've removed Br2 and I've replaced it with an OH, so now I have an enol. That enol in water is going to tautomerize to give an aldehyde, right? So now notice the double bond is on the carbon on the right-hand side, so I now have an aldehyde. So instead of a ketone, I get an aldehyde. So again, this is sort of like an anti-Markovnikov type of addition reaction where the carbonyl is forming on the least substituted carbon instead of the more substituted carbon. Let's look at an example. So if I take, here I have 1 pentyne, and remember, if I react this with water and sulfuric acid with mercury sulfate, which we just saw in the previous video, then what's my product? I get a ketone. The double bond, right, the carbonyl forms on carbon number 2. So I get this, ketone. Now, notice what I can do here. If I take that same alkyne, 1 pentyne, treat it with HBr2, where the R's are, sterically bulky alkyl groups, followed by hydrogen peroxide, sodium hydroxide, and water, right? So the mechanism is the same as we saw in the oxidation of the alkyl boranes when we treated them with, when we hydroborated alkenes. So now the product is an aldehyde, right? That where the carbonyl is now on carbon number 1. And since carbon number 1 has a hydrogen on it, then we're going to get aldehydes. And Generally speaking, this type of reaction can really only be used for terminal alkynes. If I used an internal alkyne, I would get the same result as I get for a simple hydration reaction of an alkyne. So the only main difference is when reacting a terminal alkyne, now I can either put it onto the more substituted carbon or the least substituted carbon. And so that's not a nice little twist on the regio selectivity of these reactions.